That's how you know
Very
it's
tired.
tough. Like if you can get
Incredibly
like an
tired.
88 on it, that's how you
I'm
know
a.
you can finish it.
What are you making? Yep.
I got like a 60 something.
Have you ever seen the movie Stand and Deliver? Alright. Watch the movie Stand and Deliver, and then we'll talk about why your calculus class is at 8:30 in the morning.
That's crazy that you got an A class. Yeah, you suck. You're so good. You know, in terms of nerd though. I don't really have that test. That test was long enough for like 2 years. Wow, good job. Yeah, she packaged them.
Oh, that's what I forgot to do. I meant to print out more copies.
I piled up all my old stuff from the term before, and I still haven't gone through it. There's a bunch of long and meandering note sheets that I have to go through.
Yeah, I have those. So probably like during lab today is a good time to go over that. Where are these notes not updated? I know some people have work, so.
Look at all those summations. Huh? Looks like there's some. Yeah, there's Heisenberg in here. But up here, there's a bunch of summations.
Right.
Take it we're going to be learning some of this math?
No.
Oh,
That's what all the pretty pictures are for.
fair enough.
We're taking a pretty picture approach.
At what point will we be learning that kind of math?
Oh, like PChem kind of maybe.
tastes like somebody whispered strawberry into a glass of water.
Yeah, I like LaCroix.
I don't like them because there isn't enough flavor.
That's funny.
I don't need sweetness. I just need flavor.
All right, let's get started here. Are there any questions before we just kind of dive into lecture? No, feeling okay? All right, so we left off just kind of reorienting ourselves. So we were going through our 6 electron pair group. So hopefully you have our cheat sheet out. Oh, I should update this, by the way. So sp3d for our 5 electron pairs. sp3d2 for 6 electron pairs. And again, just a reminder that we're not actually making any d orbitals into here, but this is just a reference to the parent electron geometry there. So again, we were at octahedral. So we had just finished up our boron pentachloride here and determined it was square pyramidal for its molecular geometry, which again means that it's part of our octahedral electron geometry. Questions on this one where we left off? Again, everything kind of making sense. All right, let's try kind of our last characteristic compound here. And so these I don't have good examples for. They kind of exist in theory. If you can come up with a good example, maybe extra bonus points or something for you. But yeah, the last one we'll do is our square planar compound. And you can maybe guess what the characteristic compound would be. But see if you can come up with your correct Lewis dot structure for xenon tetrafluoride there. So I see mainly good structures. Just again, double check those total electron counts. And so I'll kind of go over another way to look at this. So right, we can look at this. So xenon is one of our noble gases, so 8 valence electrons, and then it's bound to 4 fluorines, right? And then we can tell that this is just a normal bond. Remember our fluorine, you can kind of think of this in your mind if you need to, right? So fluorine, 7 valence electrons available to make 1 bond. And so now you can kind of piece together, okay, well, my xenon has 8 valence electrons. That means 4 of them are involved in bonding. And so many of you did that, drawing out our nice square planar shape. And then don't forget that we only have 2 lone pairs. So again, write 1, 2, 3, 4 valence electrons in bonding, and then 1, 2, 3, 4. So 2 lone pairs there. Again, giving us our appropriate shape. And then fill in your electrons. Obviously, you could have also totaled up the total number of valence electrons and gotten the same answer. I'm just trying to show you different ways of kind of seeing it, right? See your electrons, where are they going? How are they involved in bonding? Kind of electronic bookkeeping there. So excellent. And then other observations. Obviously, we expect this since xenon is a noble gas, right? So it was already satisfied by the octet rule, so now it's hypervalent. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons that xenon is feeling. Then everything else satisfied by the octet rule. And then, so what's our electron geometry again? So octahedral, good. And then what's our molecular geometry? So square, planar, excellent. All right, so that pretty much covers it, like I said, for kind of characteristic compounds. And again, this is our kind of AX4E2. And obviously, again, you could change these out for any other halides, maybe hydrides, although I don't know that you would get xenon hydride. We'd have to see if that exists. All right, so let's look at other kind of helpful things that we can derive from this. And I think we went over kind of polarity last quarter, but it never hurts to kind of look at it again. It's in this chapter. And again, we want to see how we can use our little chart here to help us. And so now let's look at let me start a new page here. So now let's look at polarity again. And so let's try this compound. So bromine, trifluoride. And so see if you can determine whether it is polar or nonpolar. So how would you do that? Maybe draw out the Lewis dot structure would probably be my suggestion. So look at your structures. So double check your structures if you're looking at them. So make sure that you don't have anything funny going on, right? So how many bonds does fluorine typically make? So 1, and then how many lone pairs then should we end up with on bromine? So 2. So double check your shapes on this. I was kind of walking around and seeing funny geometries or missing lone pairs. And again, right, look at other ways to kind of bookkeep your electrons. So 7 valence electrons on bromine. So 1, 2, 3 involved in bonding, and then the other 4 are lone pairs there. And so looking at this, what can we determine? So can we tell yet if it's polar or nonpolar? Well, not a charge, but yeah, they're greater area of electron density, I would say that. So yeah, that's a good clue that it's probably polar. But what else kind of tells us that? So that's a good hint, yeah.
If you think about the structure of it, the electrons that are on that side are going to be repelling the fluorines, and that's going to, I think, create a kind of going to make it polar.
So yeah, so same arguments, right, of just again looking at the electron cloud. But is there another, you guys aren't wrong, but is there kind of another way to kind of be more confident in that? What do we notice? Kind of, I'm trying to hint at the symmetry element here. Yeah, so it's asymmetrical, right? So we kind of have broken our symmetry in terms of our fully symmetric. And so that's kind of the other clue, is we can go back to the parent group, right? So 5 things attached to it. And so if it had all even fluorines all around or all similar atoms, right, if that they were close enough in all electron negativity, then that would be fully symmetric. And then once we break this symmetry, then we have, right, a higher chance of being polar. And so good, and again, right, just kind of recognizing too where that region of electron density is, that also helps. So you can kind of visualize this. And so now that you've or you will have an introduction to WebMO, right, you could knock yourself out and start trying to model these different compounds. You can play with the orbitals. So next week I'll kind of show that with WebMO, and we'll look at that with our diagrams. But this can start giving you, again, the pictures of these orbitals. Yeah. I mean, if they, somehow the dipoles still canceled each other out, right? So you're making sure, so, right, if you were taking this more rigorously mathematically, right, you're doing the vector analysis for everything. And then, right, we would say, okay, well, it's pulling more in this direction, so the vector is going more here. Yeah, so then that could still be, yeah, nonpolar, exactly. So that would be an exception. But again, you could have different atoms which could break the symmetry. But yeah, so that's where you still gotta watch out. And then with that too, you can always kind of sanity check yourself. And so don't forget, right, you can kind of look up a compound, so bromine trifluoride, and then again, just to get a sense, especially while you're practicing, we can look up the dipole moment. And I would say if it's generally over 0.5, that's a good indication that it's polar. Again, you kind of want to get a sense of different compounds, which is why I encourage you to look at this. But so bromine trifluoride, 1.19, so that's pretty significant. And again, that's the dipole measurement, so a physical measurement. All right, so that was good. So then let's practice with phosphorus pentachloride. So then go ahead and tell me, is that polar or nonpolar? So our Lewis dot structures are looking good. So I'm seeing everyone drawing those pretty consistently. And so now looking at this, so polar, non-polar, what can y'all tell me?
It's going to be non-polar because we can tell that it's going to be a trigonal bipyramid, which is symmetrical.
Excellent. And I heard a lot of people yell that out loud. So again, just recapping, fully symmetric, trigonal bipyramidal, same atom right on everything. Or again, they could have been similar electronegativities. Excellent. So does that feel clear? Feel better? All right, let's try a few more. And again, this tells us about their properties. So what about ammonia? Is that polar or non-polar?
When determining a compound, whether it's polar or non-polar, can I also calculate with the electronegativity, or in this case?
Oh, so that's a part of it, but we're also looking at more like the breaking of the symmetry in this case. So yeah, it's not like inappropriate to look at it, but like generally we're kind of comparing the differences in bonding, right? Because we're going to see the carbon tetrachloride versus methane, and you'll see, right, you can measure the electronegativity difference of the bond, right? But you still have to consider that, yeah. All right, so it looks like chat has an answer. So what do we think for ammonia? So polar, excellent. And so, right, we have this nice lone pair. That's obvious. So, right, you could say, okay, we have our region of electron density here. We could note that it broke the symmetry. So again, right, it's from our tetrahedral electron geometry, but we broke it, right, such that the molecular geometry is trigonal pyramidal. And so again, that breaking the symmetry changes it. So excellent, polar. And then just thinking about the properties of ammonia. So like dissolves like. And so, right, you can dissolve ammonia in water. And again, we'll kind of look at this acid-base chemistry a little later and what this lone pair does, right? But that's kind of giving us a hint of like, that's why it goes into water, because it is polar and it can, have interactions with it. And so let's compare that. So now let's do these 3 compounds of methane and then dichloromethane versus carbon tetrachloride. So compare those, right? Polar or non-polar. So what do we notice about all these three compounds? What do they have in common?
They all have a central carbon.
So central carbon, and then what else? So tetrahedral, excellent. So we're comparing that, right? So then they're all fully symmetric in some sense, but well, let's look at these compounds. So which one is not symmetric, I guess we should say? Yeah, excellent. So our middle one, dichloromethane, and always good to correctly practice pronouncing the names. Just this is always my fun fact. Like seriously, you should get into EH and S because sometimes people are like highly unqualified. Because one time I had like a EH and S guy come in because dichloromethane. This is the one I think I mentioned it last quarter. It gives you like the DCM burn. It's kind of toxic, so. Anyways, it's carcinogenic, so sometimes people will go around asking if you work with it. But this guy did not know how to pronounce it, and he was like dichloromethane, and I was like, okay, you clearly have no idea what's going on, and you've never worked with this compound. But anyways, so yes, this one is not symmetric. Excellent. And then, like the question was brought up earlier, so now that it's not symmetric, right, this is where we might want to look into their difference in electronegativities. And so obviously, right, the CH bond tends to be more nonpolar. And then we have our electronegative chlorine there. And so we would draw our vector, right, that it's pulling more towards our chlorines. And then, of course, we could also kind of draw this out with some sort of electron density there. And so then that makes this one what? Polar, excellent. And then by symmetry, these two should be nonpolar. Yeah, question? Of the dichloromethane, or yeah, it doesn't matter. You can, yeah, so you can spin it in any direction. And so yeah, like prove that to yourself too, right? Like you want to get better. I didn't bring my molecule kit today, unfortunately, but right, that's just something you want to practice. Is like, is it the same? Like, kind of pop it around and just like be familiar with that. So that's good because that's coming up, kind of in the chapter, being able to recognize isomers or not. And it is challenging, right? Seeing in 3D, so you just want to keep practicing that. Use your molecule kits. Next week, I'll try to remember to bring my baby OChem kit so you could see that one in person. And then again, right, we can double check our dipole moment. And so we'll look at carbon tetrachloride just to again confirm, right, dipole moment of 0. So yes, right, all those vectors do cancel out mathematically, just like we would expect them to. Oh. That's service there. All right. Let's see, what else should we look at? Sorry, question? Well, ionic compounds are like completely different. Yeah, because we'll touch on that a little later, and by touch on it, we'll like really briefly touch on it, because ionic compounds go through different like what's called packing crystal structures, and that has like separate considerations, right? And then they're not connected in the same way. It's just like how those things pack. All right, so on that note on how to look at this, let's switch to isomers. And so first we'll look at kind of structural isomers. And so structural isomers, I'll just give the book definition, is when we have the same formula, but then different bonding or connectivity. So this would be right, you'd have your molecule kit and then you completely pop off everything and completely disconnect it. And so a good example of this, of some isomers, are going to be propanol. And this we should generally clarify as N-propanol. So N just means our straight chain. And so prop means 3. And now this all refers to an alcohol group. So somewhat touching on OChem here. And so then we can draw this out. So this is our straight chain. And there's a few different ways to represent this. So you could see this kind of drawn out more explicitly, like so. And then our OH, so note 1, 2, 3 carbons. Carbon has to make 4 bonds, so then you fill in any remaining bonds with hydrogen. Notice, though, that this is nice and simple, right? So you can see the connectivity, but the geometry is completely ignored here. So I just like pointing that out. And so O chemists will likely abbreviate, so 1, 2, 3. So 1, 2, 3 carbons, and then my OH there. So this is another way to draw the same compound. So this is still N-propanol, still straight chain, just so you can kind of appreciate the 3D geometry. And again, could be a good time to look at the internet. Like that's what's kind of the beauty of the internet, is we can pull up a picture easily, right? And again, appreciate, oh yes, tetrahedral, 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 right? So I want you to be thinking the hybridization essentially at every carbon, right? sp3, sp3, sp3. So good, just keep that in your mind there so you know what it looks like. And so let's compare this to its isomer. So versus isopropanol. And so now this iso refers to this little isopropyl group, 1, 2, 3. So this is the abbreviated form of isopropanol, or this is now just the right household isopropyl alcohol that you would buy, so rubbing alcohol. Obviously, usually you purchase it commercially as like 70%, so mixed with water. And then we could also draw it out again, kind of in this more explicit format. But again, right, you're kind of noting that different connectivity. So our OH is instead attached to our middle carbon as opposed to our N carbon there. And so that's structural isomers, and we could come up with probably other isomers. You can play with things like making an ether. On this one?
Yeah, because like the line structure or whatever, it has like that Y shape, so you wouldn't like.
I mean, that's not how they draw it. That's why there's like criticisms of the structure, right? So you may see it like that, but what you're really wanting to think of like tetrahedral, right? So it's not really like this Y there is because it's a tetrahedral, and then the little hydrogen is not really shown in this structure, right? So it's more of a tetrahedral shape.
So it's more of the Y shape than it is the.
Yeah. Yeah, because this is more like an oversimplification, so you can see the connectivity better versus, again, kind of truly seeing the 3D geometry. Okay, a little slow to build that. Let's look at, well, actually, before we move on, and we won't do this right now, but you could come up with other isomers, so like hexanes, or that has a whole bunch of other isomers. So hexanes Generally, if you were to buy hexanes, why it's called hexanes is because it's literally a mixture of all the hexanes. And so you have 1, 2, 3, 1, 2, 3, 4, 5, 6. Always count and then double count your carbons, especially for OChem. And then you could go crazy, 1, 2, 3, 4, 5, 6, making all your isomers, 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, 4, 5, 6. So not all inclusive. So just kind of showing you again, right, different connectivity, but all hexanes, all same formula. All right, let me see if I can make a model real quick. So now we'll look at our geometrical isomers. And so I know people were kind of playing with this in lab.
Butane, just another name for a hexane?
Butane is 4 carbons. So yeah, but yeah, we'll get into a little bit of OChem, I think third quarter. We'll at least like dip our toes in naming. Sorry. All right, so now we're looking specifically, at least for this moment, at our octahedral compounds. And so now I'll draw this out as well. And so now this is under geometrical isomers. And so we have, looking at our octahedral compound, so again, I'll draw it out. What do I want to put in the middle? We'll put sulfur. We'll put sulfur, and let's just we'll put a fluorine on our axial position. And this is again how I've kind of have our little model that we're looking at. And then let's say we have chlorines. And so we're looking at these two groups, right, our two odd man out essentially. And so they're across from each other. And so this would be called our trans isomer. Again, when they're across. And then versus, so right, we could pop this off physically and get our other isomers. So we only have 2 by rotation, right? So you can keep kind of rotating around and around. But basically, so now they're next to each other. And now I'll draw this out. So sulfur, fluorine, and then it doesn't, like I said, it doesn't matter which one we switch out. It'll all be the same by rotation. So now one of those fluorines is on our middle position here. And so now when they are next to one another, and again we have 2 versus 4 atoms, this is called our cis isomer. And so there would be spectroscopic differences between them, so we're not going to get into all that today, but you would be able to tell the difference spectroscopically, so they would have different color shifts if this was a colored compound, or you could do IR spectroscopy or some sort of identifying thing to distinguish them. But they would certainly be distinguishable, is the point. And so then let's look at kind of other situations. And so let's kind of look at our pi bond again and what this means. And so we have these 2 isomers. And so the important thing to kind of think about, and maybe it's kind of, maybe let's take a step back for a second. So now let's think about this. And maybe let's look back at our notes for a second and think about CO2. If I can find CO2. So let's look at kind of CO2 for a second and go over, right, our hybridization again. So we're just kind of going over that. Okay, so we said we had CO2, and then we said, okay, well, we have a single bond. And, well, sorry, let's get our hybridization. And so our oxygens with our two lone pairs, and this is a good recap. So we said that each oxygen is sp2 hybridized, right? So again, s plus 2 p orbitals. And then our carbon was sp. Again, our other oxygen, sp2. And okay, so we said we had our sigma bond. And so the important thing is, so your sigma bond is head to head, right? So your single bonds can rotate. So you have rotation through your single bonds. But now let's look at our double bonds and kind of look at why we do not have rotation, right? So let's think about where that pi bond came from. So again, right, we have our sigma bond, so that's our first bond. But now, like we had determined, so let's just call it, I'm going to call it py today. I'm not sure if I'm consistent. I probably am not. But let's just call it py. So again, that's our available orbital, right? We had said, well, pz went in there in our mixing. And I'm just calling it px, but px mean there in the, went in there. And so py is available. And so again, right, that means carbon is also has this available since it's only sp hybridized. So right, carbon we did mention has an extra px just chilling. And then oxygen, so again py. So there's our through space pi bond, but then why can't we rotate? What would happen? Not closer, but
Like if you were trying to do that and then it just wouldn't allow because they would repel each other.
yeah, so right, it's basically not allowed, right? So they have to be the same, yeah, same alignment, right? So same, basically shading, we'll say it for, or, you know, because we're really representing how the orbitals are matching, right, mathematically. So you're trying to like look at all the mathematical combinations. Okay, they have to be in phase. But yeah, if we were to rotate it, like you were saying, it would break this symmetry. So then it would not make a bond. So that's why you can't rotate double bonds. So once it's made, it's made. And the molecule kits do attempt to like somewhat show this. So if you recall, right, so when making a double bond with these kits, that's why these ones have these kind of elongated ones. And then you make your double bond once I force it in. Right, and then we can tell, okay, yeah, we can't rotate that. But not all kits are the same. So this one does emphasize that. Like I said, I need to bring in my baby OChem kit, but the baby OChem kit is deceptive because it does rotate. So that's why I'm like, be aware, right? Think about what bonds. So when you have a double bond, you cannot rotate that bond. Okay, so now we can go back to this example and understand why two distinct isomers exist, right? Because again, they're not interchangeable by rotation. So we can't break that, at least not easily, right? So again, if you did some energetics or you did some reaction, right, you can flip it, but it's not easily done. So again, you don't really see interchange of these two isomers unless there's some sort of pathway. And so then when they're on the same side like this, so chlorine, chlorine, again, same side, that means this is called our cis isomer. And then opposite sides, that's once again called our trans isomer for this case. And then just put in your hydrogens in case that's not clear there. And so now let's look at our kind of last isomer. And so these are called our optical isomers or stereoisomers. And so let's look at an example. It's pretty famous. Well, before we look into our example, so let's look at what we need to have a stereocenter. So a stereocenter, so let's draw out an example. And so you have to have 4 different things attached to your central atom. So generally carbon, when we're looking at these, so we're generally looking at organic molecules, so write that down. So 4 different groups. Sometimes this like different group can be difficult to distinguish. You could be looking at like a ring molecule eventually in OChem, so you would kind of have to see whether that ring was symmetric or not at that certain stereocenter. But this one is a little easy to see, so let's kind of see if I can make my kit. Uh-oh. Might be having internet errors. I'm not sure how the stream is going. All right, so we're looking at, so I'm just trying to build one of my isomers. And again, this is a good one to kind of play with in lab. And so I'm trying to build my stereocenter. And so the easiest way to define it is these are what are called non-superimposable mirror images. And so, right, you can take your hands. Obviously, your hands are good examples of kind of your natural isomers, right? You can't superimpose your hands on one another. And then, so I'm still trying to make my kit, but we can draw out, so if we pretend this is a mirror, and then we flip this along our mirror here, and then, right, we can make our compound. So sorry, still trying to put on different colored balls here. Dropping things. This is also my helpful hint for when you get to OChem is like have all your stereocenters built so you're not scrambling around on the exam. So blah. Have it oriented funny. Oops, sorry, I swapped one. And of course, when you play with these kits, you have to make sure you don't obviously build the same one. And so again, right now we have mirror images. Hopefully my stream's still running. And then right now we can try to rotate it. But again, right, non-superimposable mirror images. So we can cycle those around. And so then, right, why do we care? So there's a famous example of kind of why we care about stereocenters. So they can react in different and unexpected ways. And so this was, again, a pretty famous drug that incident happened. And so let's look at this compound. So this is thalidomide. And so this was a drug that was marketed around the 60s for pregnancy, for anti-nausea. And so it was supposed to help with pregnancy side effects, or sorry, with pregnancy, symptoms, and then it was found to cause severe birth defects. And so part of the interesting thing is, so the problem with this compound, and what you should always be aware of if you were to go into like drug design and chemistry, and obviously something that they have to be aware of, is what stereocenters do you have, and then can the compound interchange between these two stereocenters easily, and then do they kind of react the same? And so it's kind of scary and also fascinating. So let's kind of go through where it talks about it. But basically the problem is that they interchange. So even if they were, I forget which version is the safe one. But even if you have like the safe form, it's going to change in your body to the other form and then, of course, produce a bad side effect. So that's what it means by here, the racemization. So that just means interchanging between the two isomers. And so in vivo, so obviously that means in the person. And so obviously, that was a problem because sometimes synthetically, you might be able to isolate one isomer, but then obviously if the drug is just going to go back and forth to the other isomer, well, that's a huge problem. And so obviously the drug was pulled, but this is kind of the characteristic example of why stereocenters are important. And so again, many drugs have stereocenters, so have to be aware of that synthetically. A good natural example too is, of course, your amino acids. Again, we'll look at amino acids kind of more in third quarter, but just kind of looking at this. So every amino acid, except for glycine, since it just has a hydrogen here, but every amino acid otherwise has a chirality, so that would be the chiral center. And there's obviously the natural form of amino acids versus the unnatural synthetic form. So different handedness of life, which we've gone over that paper in here, right? Norden, the chirality paper. I feel like I've talked about it before. Okay, maybe we haven't talked about that paper. I'll bring the paper so we can kind of look at chirality. I don't know why I thought I shared that, but all right. I think that's pretty much the end of our chapter for today. Unless there were any other kind of questions or anything else. All right, so we'll probably stop here. So like I said, those of you that are new to the class, it's kind of our typical format for Thursdays is we do a shorter lecture, and then typically we do a 10-minute break, and then hand out the quiz at that time. And then the rest of the class period is yours. So like I said, this week's quiz is super easy. Otherwise, normally you'd work on the quiz, and then the rest of the time you can work on homework, ask questions, use this time kind of wisely. Take advantage of me while I'm here. Oh, and then otherwise, I was going to say, if you need to meet me for office hours, I can generally be on campus Monday, Wednesdays, or Fridays, but email me just so I know exactly when to be in my office. I know everybody's schedules are pretty wild and variable. We can also meet by Zoom, meet by whatever means necessary. Nights, weekends, I'm also flexible, so just reach out to me early and often for help. I'm generally your best resource. I think most people found that out last quarter, that unfortunately the tutoring center does not really have tutors for this class. So you're stuck with me, but use me. I'm here for you. All right, so I'll hand out the welcome quiz. Like I said, it's super easy. And then obviously you're more than welcome to leave. Otherwise, take advantage of myself as your research. Oh, I was also going to print out more periodic tables. I forgot to make nice, pretty ones. So I will try to get some of those going, especially for those who weren't in the class. That might be 2 minutes.
Whether or not you want to be in our study group.
Whether I want to be. It depends how much bribery. All right, any questions online? Otherwise, I'll stop the stream.